Coming to 217, mark 115, increasing to 2/3 impulse. Sir, the Klingons are flanking us, attempting to draw us away from the Enterprise C.
Hold course, Mr. Crusher. Continue to fire all phasers.
In the last presentation, we used a simple geometric argument to find the location of the bright fringes and the dark fringes for the interference pattern from a double slit, really from 2 point sources that have no spatial extent. So in this presentation as well, we're not going to look at the effect of the finite width of each slit. We're pretending that each slit has an infinitesimal width. What we'll do now is actually develop the formula for the intensity anywhere on the screen. So rather than just finding the y coordinates of the maxima and the minima, we can express the intensity as a function of position along this screen. And we'll do that with a little bit of geometry and this useful mathematical device called the phasor, which some of you may have seen already in AC circuits if you've taken electricity and magnetism. And many of you will see again. If you go into physics, you're going to see something much like phasors when you study quantum mechanics. If you major in electrical engineering, you'll definitely see them in circuit theory. Okay, so even in this graphic, we can see that the finite width of the slit, of each slit, has an effect on the distribution of intensity. Notice that there's no intensity going off in this direction. So if we asked for the intensity on the screen right here, it would be 0, since according to this graphic, none of the light energy is reaching the screen there. But we're going to ignore that fact. Let's not worry about the fact that you can see the intensity of the fringes is decreasing. See how the central bright fringes are brighter than the ones at the edges, and presumably if you go far enough away from the center, you wouldn't see any of the bright fringes. Here's the function that we're going to use to describe the ideal intensity pattern from 2 point sources. That's where we don't worry about the fact that the intensity really drops off as we move away from the center. It looks kind of like a cosine curve or sine curve, but we're going to see it's really cosine squared. So as I mentioned, this gradual drop off in intensity as we move away from the center, that is a consequence of the finite width of the slits. We're not going to attempt to explain that in this presentation. We're only after this function. And I wish I had a graphic with this superimposed next to the fringes. This does a pretty good job. So just imagine that we've ignored this decay so that the value of the intensity is the same across the screen. And you can see that the peaks in the curve line up with the bright fringes, and the zeros of the intensity versus y-coordinate curve, those zeros line up with the dark fringes. This is the function that we're seeking. I1, it's important to clarify terms here. I1 is the intensity which would be incident upon the screen everywhere due to a single slit. So if we only had one slit being illuminated by this laser beam, let's say, then the intensity would be uniform across the screen and it would have a value I1. Also shown in the graphic here is the average intensity, which of course would be 2 times I1. So if it weren't for this phenomenon called interference, which results from constructive and destructive interference at different places on the screen due to the path length difference, if it weren't for that fact of superposition, then you might expect the total intensity everywhere on the screen to simply be double the intensity that would result from a single slit alone. And that's what's being showed here. So this graph is already telling us that the intensity is being focused in some directions. That's where the bright fringes are. And it's being destroyed, I suppose you could say, in others. Hopefully you can tell from this graph that the area under this wiggly curve is actually equal to the area under this average intensity. And when I say under, I'm actually referring to moving to the right. So here's the area that I'm shading, so to speak, under the average intensity. Let's show where this comes from. Do you need to memorize this? Honestly, I don't have it memorized. What I have memorized is the steps leading up to it, and I actually find that easier. And you've already learned most of the steps. Okay, so this is the intensity pattern versus y coordinate from two slits, a double slit being illuminated by something like a plane wave. Think of a laser beam. We've looked at this setup in detail already. The field point is far enough away from the slits that we can pretend that these rays are parallel. Well, let's not forget that those rays actually represent electromagnetic waves. Those are, I'm not going to say plane waves because it's more like circular waves being emanated by the slits. But the waves have electric and magnetic fields, which are perpendicular to one another. And I actually prepared these slides incorrectly. I had the electric field in blue, and then I used the right-hand rule, and I thought about Poynting's vector and realized that I had chosen the wrong one. So you can use your right hand to confirm that if the wave is traveling this direction, then it must be the electric field, which is red, right? Put the four fingers of your right hand along the red vectors here, curl them towards the blue, which would be the magnetic field, and my thumb does indeed point in the direction of travel of the wave. If you try to make the blue field the electric field, it doesn't work. Your thumb would be pointing the opposite direction. Okay, so here are the two electric fields from these two separate waves, the waves from the two slits impinging at the same point on the screen. Now, I drew them offset just a little bit, but you can imagine these electric fields arriving right here. And you'll notice that they're not in phase. Let's just assume that they have the same amplitude, by the way. Yes, one of them goes just a little bit farther than the other, but the difference is so small, we don't need to worry about the inverse square law. So there's no significant change in amplitude because of the extra path length difference. Okay, so if they have the same amplitude, E1 and E2, then clearly they're out of phase. One is towards its peak value, and one is clearly not. So here's how they might be changing in time. Let me go back and do that again. Right? They're both oscillating sinusoidally in time. If you were to park yourself right here and observe how those two fields change in time, they're both oscillating sinusoidally, but they are not necessarily in phase. They're not necessarily peaking together and going to their minimum value together. If they were, we would call that max constructive interference because they would add rather than subtract. On the other hand, if the path length difference were such that one of them peaks when the other one's at its max negative value, this is somewhere in between, right? This one's almost zero while this one's at its max value. Well, what if this arrow were pointing the other direction while this one was at its max? They might cancel to some extent. So that's the phase difference that we're talking about. And it's a phase difference due to the path length difference, because keep in mind throughout this discussion, at the source, they are in phase. The inherent phase difference is zero because these slits are being illuminated by the same plane wave or laser beam. Okay, so now let's introduce the phasor, which is not a super modern science fiction weapon mounted on a spaceship that goes pew, 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 pew. Not that kind of phasor. It's named such, I believe, because we're talking about a rotating vector that's got a particular phase. So I'm going to present this slightly differently from the way your book does. I don't want to call this phasor a vector, because let's use the word vector to talk about the physically real, the actual physical quantity, the electric field and the magnetic fields. Those are vector fields. The phasor is like a vector in that we represent it with an arrow. So in this picture, this is the brown vector is the phasor associated with the field. So it has a direction, it has a length, and you could even think of it as having an X component and a Y component, but I don't want to call it a vector because it's mathematically distinct from the actual electric field. So here's how it works. We choose the length of the phasor to be equal to the amplitude of the field in question. Right now, I'm showing you the phasor for the electric field from source 1. The projection of the phasor onto the horizontal axis, this projection right here, that tells us the instantaneous value of the electric field. In other words, what's the electric field at this point in time? Because we're going to set this phasor into rotation. So this red component, the projection onto the horizontal axis here, is what we think of as the actual value of the electric field. And this number theta here is what we call the phase of the phasor. Now, your book calls this in one of their diagrams the x-axis, and they call this the y-axis. I'm not going to do that because this phasor doesn't actually exist in space. It's not, it doesn't exist in R3 and it's got components in the x and y direction. That's misleading. The electric field is what exists in space. It does point in a particular direction. It tells you the direction that a charge would be pushed if placed in that electric field. So that's physically meaningful. The phasor does not exist in space. It's a mathematical convenience. So what do we do with the phasor? We put it into rotation counterclockwise. And we let the phase, theta, be proportional to the time. Omega is the angular velocity. Not coincidentally, it's the same omega that would appear in your progressive wave function, kx minus omega t. It's the same omega. So as time advances, obviously theta advances, and it does so linearly. So if theta is increasing in time, that tells us that this phasor is rotating. It's rotating counterclockwise as time goes forward. So we could just replace the theta by omega t. So let's see what this looks like. I used my superior animation abilities to string some slides together. Notice that the phasor doesn't change length. Let me go backwards in time. See that the brown phasor never changes length because that length represents the magnitude of the electric field. What is changing is the horizontal projection. So right now we would say that the electric field is positive. Whatever direction the E field points, from that wave that's impinging on the screen, let's just call that the positive direction at a particular moment in time. Eventually, it's going to shrink to 0 and then point back the other direction. That direction would be the polarization direction of that particular electromagnetic wave. But the point is, the projection, this is the representation of the actual field, it's oscillating in time. And that's what this phasor accomplishes for us. Now, we haven't seen the real power of the phasor yet, but at least we can see how the horizontal projection of the phasor tells us how the actual physical electric field will change in time. We get that oscillatory behavior just by putting the phasor into rotation. The other component, we throw it away. We don't need that for anything. We're only interested in the horizontal projection. I shouldn't say we don't need it for anything, because when I go into Python and do some simulations, I will use it for something. Okay, what am I doing here? Yeah, so here's some background information that you don't need to stress about. If you don't understand the next minute of this video, that's fine. I'll let you know when we're getting back to what you really need for this class, but it's worth pointing out that this phasor is really another name for a complex number. Like I said, those of you who go into greater depth in physics, if you study quantum mechanics, or if you're going to take electrical engineering classes, you'll see phasors again, but they will likely just be called complex numbers. So I'm using the arrow symbol here for this phasor. Arguably, I shouldn't use that arrow because we usually reserve the arrow for vectors. Like this kind of looks like I'm talking about the electric field. I'm not really talking about the electric field here. I'm talking about the phasor. The electric field comes from the horizontal projection. I'm using the arrow symbol for the phasor because, well, we're also drawing it with an arrow. E1 here is the magnitude of the phasor, that's the length. And then this quantity here, this is the base of the natural logarithm, that's approximately 2.72, and a bunch of digits after that. e to the I omega t. If you have not yet encountered Euler's identity, if you have no idea what it means to put an imaginary number into the argument of the exponential function, don't stress about it. Like I said, we don't need this. But what this number actually means is you go this far along the real axis. We're all familiar with the real axis. And then you go this far along the imaginary axis. So the phasor actually gives the location of a point in the complex plane. The complex plane is a lot like the xy plane, except the x coordinate is the real part of your quantity, and the y coordinate is the imaginary part of your quantity. It's a lot like the number 1 plus I. 1 is the real part, I is the imaginary part. All right, we're not going to use complex numbers in this semester, but I thought some of you would be interested to know that a phasor really is just a complex number where the phase depends on time. So the argument of the complex number is what we call the phase. And surprisingly, or not surprisingly, depending on your math background, when you plug a pure imaginary number into the exponential function, what you get out is sine and cosine. Whoa. So this is a real quantity. Cosine of some real number is a real number. And then the sine of some real number is a real number. Well, I times a real number is an imaginary number. So what we have here is a complex number. Cosine phi, that's how far you go along the real axis. Sine of phi, that's how far you go along the imaginary axis. So think of this as like the x and y coordinate of a point in the complex plane. But I really shouldn't say x and y because it's the real and the imaginary parts of a complex number. It works the same way as the x and y coordinates of a vector in the plane. So I'm not going to call it a vector. I'm going to call it a phasor. And if you're just baffled right now thinking, why is this true? Why would you get sine and cosine out when you plug imaginary numbers in? Well, it's not obvious at all. There's no reason at all that should be clear to you. There's a number of ways to show it. One way would be to use the power series expansion for the exponential function. And after you do that with an imaginary argument, you can identify within that power series expansion the power series expansions for cosine and sine. That's one way to do it. Let's not dwell on that. Let's get back to phasors. Here's a nice GIF showing you the meaning of the phasor. So the phasor is the blue rotating arrow. If we're talking about the electric field phasor, then the physical field, the oscillating electric field in time, is given by this horizontal projection. It's too bad it's not color-coded, but look at the horizontal projection onto the horizontal axis. That's the value of the field. And then if you were to plot the value of the field versus time, you would find that it's oscillating sinusoidally. So it's perfect for our purposes. It describes how the electric field from a sinusoidal progressive wave actually does change in time at a fixed point in space. Okay, so why are we complicating things like this? Because we were already able to describe electric fields perfectly fine with just sine and cosine progressive waves. Why do we need these phasors? The utility of the phasors becomes evident when it's time to combine electric fields. So we've been talking about the double slit experiment, or the two-point source experiment, where both sources produce waves with an inherent phase difference of 0, and we have to worry about the path length difference. We look at the field point on the screen. One of the waves may have gone a slightly greater distance. Okay, so now we've got two phasors, one for each of the fields. This is the phasor representing the electric field from slit 2. This is the phasor representing the electric field from slit 1. And a moment ago, I said that the angle, or maybe I didn't make this clear, but the angle that the phasor makes with the horizontal axis, that is the phase of the wave. So as time increases, the phase increases, your vector continues to rotate. Well, I'm acknowledging that these two electric fields at the field point P on the screen may have different phases because one of them may have traveled farther. So delta phi is that extra phase. It's the phase difference between the two sources. Now, in general, we've talked about this. This could have two contributions. There could be the inherent phase difference plus the contribution from the path length difference. But we've already assumed that delta phi sub 0, the inherent phase difference, is 0 because they're both being illuminated by the same light source. So this delta phi here is really the phase difference at the field point on the screen. It's the phase difference between the two electric fields due to the path length difference. And that's why this vector points in a different direction from, I should say phasor. This phasor points in a different direction from this phasor, even though I've drawn them with the same amplitude. So if they had the same phase, if the phase of E2 was also omega t, then it would point off in this direction, same as the direction of E1. And this makes it a little bit clearer. So this angle right here is omega t. Phasor E2 has this additional shift in angle. This is delta phi. This angle here is the phase difference between phasor E1 and phasor E2. So if delta phi right here were 0, then this phasor would point in the same direction as phasor E1. In other words, they would be in phase. So notice, even though these two phasors have equal amplitudes, right? The waves arriving at the screen from the two slits, they have the same amplitude, but their instantaneous values are not the same because their phases are different. This phasor is rotated by a different amount, so its projection onto the horizontal axis is different. Right? This projection is greater than this projection. So their instantaneous values are not equal. Evidently, these two fields are out of phase, like the animation that I showed just a few moments ago. Those two E vectors were not oscillating in phase. We can see that here by looking at the horizontal projections of the phasors. Or you could just note that there's a kink here. The phasors are not collinear, or they're not parallel. So we know they're not in phase. Okay, here comes the cool part. What are we even doing here? We are trying to, that's always a legitimate question. We're trying to calculate the intensity anywhere on the screen for any y-coordinate, not just the bright fringes or the dark fringes. Well, the intensity comes from the square of the total electric field. If we want to know the total intensity anywhere on the screen, we need to know the total field. And it's pesky to be adding up cosines and squaring those, right? If each of these electric fields could be described with a cosine or a sine, we'd have to add those up and then square them. That math actually gets messy and worse than what we're doing here with the phasors. And you've already seen it. If you go back to a previous presentation, you can see how this was derived, but we'll do it more simply or more elegantly with these phasors. So here's the idea. We would like to know the sum of the horizontal projections at any time, because remember, the horizontal projections are the actual values of the field. So if you want the total field strength at any moment in time at field point P, you'd have to add up the fields from each source individually. But check this out. What we'll do instead is first find the total phasor. That's why we've placed the phasors tip to tail. So close the triangle, so to speak. This vector, which I'm going to call a phasor, this is the phasor for the total electric field. So there's three phasors here. There's the phasor that represents electric field 1. There's the phasor that represents electric field 2. That's from the second slit. And then there's this third phasor that represents the total electric field. That's really the phasor that we're interested in. Well, how do we get from this picture the value of the total electric field at that moment in time? Not the phasor, but the actual physical electric field. It works the same way that it works for the individual phasors. We just take the projection. So look at this green vector representing the total phasor and take its projection onto the horizontal axis. That's this purple arrow here. That's the value of the instantaneous electric field. And remember, what direction does this point? Well, whatever the polarization direction is. And that may confuse you because maybe you're thinking, well, the polarization could point really in any direction. That's true, but our double slit analysis is really two-dimensional. So we're imagining that and I wish I had a graphic here, that the electric fields from the two vectors are, excuse me, the electric field from the two sources are parallel. They can't just point in any old direction. Okay. So how does this picture change in time? Well, since both of the Brown vectors are rotating at angular velocity omega, then their sum, E total, will also rotate, and it will look something like this. So let me go back and do that again. Observe how the shape of the sum of the phasors doesn't change. Look at the relationship between the brown phasors and the green phasors. That doesn't change. It's just that the whole thing rotates. Well, the other thing you should pay attention to is how the various horizontal projections change. Look at the projection of phasor E1, the projection of phasor E2, and also the purple one, which is the projection of the total phasor. Okay, but at each slide, you'll find that the red projections add up to the purple projection. Same thing here. Now, in this case, the second projection is basically 0. That's why you don't see it. And now the projection of the phasor E2 actually points backwards. So it subtracts from the phasor from E1. So this would be an instance of, I almost said an instance of destructive interference, but that is misleading, because when we talk about locations of constructive or destructive interference, those locations don't change in time, right? If there's a particular point on the screen where you get constructive interference, then it's always constructive interference. It doesn't change within the period of oscillation. So I really shouldn't call this destructive interference. It just happens that at this point in time, the two field contributions are canceling each other to an extent, but a few slides before that, they were adding. So you can let this play in your imagination, and you would see that this purple vector is going to shrink to 0. Then it will, I shouldn't say vector, this purple arrow will shrink to 0, and then it will point back in the negative direction until it reaches the same length, but pointing in the opposite direction. In other words, that purple arrow is going to oscillate back and forth. And that represents the physical quantity of the total electric field. That projection shows you how the total electric field depends on time. Okay. I mentioned a moment ago, the total phase difference between your two waves from the two sources could have an inherent contribution. That's if they're being illuminated by different light sources, but that's not the case, so forget about that. It's one laser beam hitting both slits, so we only have to worry about the phase difference due to the path length difference. And let's start putting stuff together. In the previous presentation, we used some simple geometry to conclude that if the screen is far away, the rays from the two sources are basically parallel, and we can use this really good approximation d sine theta for the path length difference. So this is the direction that you're looking on the screen, the direction away from the forward direction, and lowercase d is the slit separation. Okay, the next important thing to understand about these phasors is how that phase difference, delta phi, affects the amplitude of the total field. So if delta phi were 0, if these two waves were in phase, then the phasors that we use to represent them would be parallel. This brown phasor would point in the same direction. So let me be clear here, and I didn't actually label this. What's the total phase of E2? Well, it would actually be omega t plus delta phi. The angle that this phasor makes with the horizontal axis here, this angle, is omega t plus delta phi. But right now, we're just interested in the difference between the angle that E2 makes with the axis, or the phasor E2, and the angle that the phasor E1 makes with the axis. That's the phase difference. I like to think of it this way. Imagine you're traveling along the direction of E1. It's the amount by which you would have to swing counterclockwise to align yourself with E2. That's all. It's just the extra little bend to switch from the direction of one phasor to the direction of the other phasor. Okay, well, let's simplify the picture by just assuming that we're at t equals 0. So the instantaneous phase of E1 just happens to be 0. That doesn't change the relationship between these two. It just puts E1 horizontal in the screen, which makes this easier to visualize. Okay, and we know that just like vectors, you can add them tip to tail. So the total phasor here is what you get when you close the triangle. What just happened? Well, what if the phase difference were smaller? What if these two waves were more nearly in phase? If you put this phase difference closer to 0, then you bring the second phasor closer to the horizontal axis. Watch what happens to the length of the purple vector, which is their sum. Didn't the total phasor get longer? And you can probably see that if the phase difference is actually 0, then E total, the phasor representing the total electric field, takes on its greatest value. So you get the greatest possible magnitude of the total field when the two waves have a phase difference of 0, which we kind of already knew, right? That's what we call the condition for maximum constructive interference. If the phase difference is 0, it means the two electric fields at that point P on the screen are oscillating in phase. They go up together, they go down together. The peaks and the valleys line up. That's the most constructive interference you can get. Of course, the phase difference doesn't have to be 0. Imagine taking E2, the phasor representing electric field 2, and rotating it by a further 360 degrees, also known as 2 pi radians. They would still be pointing in the same direction, and you would still get maximum constructive interference. So the phase difference between these two phasors really just has to be a multiple of 2 pi. That's the condition for max constructive interference. Rotating the second one by another 360 doesn't change the fact that they're still pointing in the same direction, which would give the magnitude of the total phasor its greatest possible value. Okay, let's look at a different configuration. In this case, the phase difference is clearly not 0. In fact, it's greater than 90. Let me increase it further still. And now you'll notice that these two phasors almost seem to subtract in a way. So their total is much less in magnitude than it was previously. Let's carry this a little bit further. And you can see that when the two phasors point in opposite directions, in other words, when the phase difference is pi radians or 180 degrees, that's when the magnitude of the total phasor actually shrinks to 0. Okay? And if the magnitude of the total phasor is 0, then obviously its horizontal projection is also 0. If you project 0, you still get 0. So this would be a scenario in which we get what's called max destructive, or even perfect destructive interference, because I happen to draw this as if the two fields have the same magnitude. And that's really what we're going to do anyway when we analyze the double slit and the single slit. Well, the double slit. We're going to assume that the waves from the two sources have the same amplitude. So if they have the same amplitude and their phase difference is pi, then the length of the total phasor is 0, and that means the horizontal projection of the total phasor is 0. Well, what's the meaning of the horizontal projection of the total phasor? That's the total electric field. So the total electric field here in time is always 0. That's why it's perfect destructive interference. Now, what happens if you rotate E2 by another 360 or another 360? You always come back so that you're pointing opposite E1. So actually the phase difference could be pi or 3 pi, 5 pi, etc. Adding another 2 pi to the phase difference is the same as just rotating E2 through a full circle. It's still going to point opposite E1, which means the total phasor is 0. I need to go back and emphasize something that I don't think I said earlier. The greatest value in absolute value that the physical field takes on. Remember, it's the horizontal projection which represents the actual electric field. The greatest value that it takes on is the length of the phasor. So right now, the instantaneous field has an absolute value less than the magnitude of the phasor, but there comes a time right about now where the strength of the field is equal to the magnitude of the phasor. So the magnitude of the phasor tells you the greatest absolute value taken on by the electric field from one of the sources. And the same applies for the total phasor. Once you find the total phasor by adding the individual phasors as vectors, the length of that phasor gives you the maximum absolute value taken by the total electric field. So now we finish this. We see the elegance of this method and how it actually saves us quite a bit of headache dealing with trig identities, because the function we're about to write down was derived earlier using some trig identities. If you can get past the hurdle of understanding the phasor conceptually, then this really does make things easier. So what about the general case? Can we come up with an expression for the length of the total phasor, because we know now that that's the greatest absolute value taken on by the total electric field? Can we find an expression for that length in terms of the phase difference? That would allow us to calculate the intensity anywhere on the screen, not just at the bright fringes where the phase difference is 0 or 2 pi or 4 pi, and not just at the dark fringes where the phase difference is pi or 3 pi or 5 pi, etc. So we see what the total electric field is in the simple cases. When the phase difference is 0, obviously the length of the total phasor is just the sum of the individual lengths. In fact, if the two sources produced electric fields that were equal in amplitude, then rather than calling them E1 and E2, I could just call them both E. If that were the case, then the magnitude of the total phasor would just be 2 times E. So for the case of max constructive interference, the total electric field is just double the field, or I should say that the total electric field magnitude is double the magnitude of each individual. And I'm kind of using magnitude and amplitude interchangeably here. For the case of perfect destructive interference, which was here, the amplitude or magnitude of the total electric field is 0. Okay, so those are the two extremes, 2 times E and 0. What about everywhere in between? That's what we'll do with this picture. Okay, your book does it one way. Let's use an identity that you may remember from way back in high school trigonometry. The law of cosines, which is not a legal law. You can't use this in court, but you can use it anytime you're doing geometry in a plane. It's irrefutable, and it's universal. It's not just US law. This law works anywhere, in any country, on any planet, as far as I know. Okay, in this picture, they're choosing to label the angles at the vertices with capital letters. So capital A is the angle at this vertex, capital C is the angle at this vertex, and they use lowercase letters to represent the lengths of the sides. So lowercase c, you'll notice, is the length of the side that's opposite angle C. That's how it works. Lowercase a is the length of the side that's opposite angle A. And there are 3 relations you can write down using the law of cosines applied to this triangle, and you would just permute the letters. So right now we're going CAB. You could then go ABC or BCA, but look how this equation works. It relates the length of side C, right here, to the lengths of the other 2 sides and to the angle across from side C. So the angle that goes in the cosine function here is the angle opposite this side. And you'll notice that that angle capital C is the angle formed by sides A and B. So this angle is the angle between these 2 sides. And to help you remember this, I like to think of this as kind of like a corrected Pythagorean theorem. You can only use Pythagorean theorem for a right triangle. This may not be a right triangle. So I like to think of this extra term as like a correction. If you got rid of this, wouldn't you just have c squared equals a squared plus b squared? Also note the minus sign. It's a minus sign. If you're going to define the angle C as the angle between sides A and B, then you must use a minus sign. Okay, well, what if angle C here was a right angle, 90 degrees? Then we would be looking at a right triangle, and the side lowercase c, which is opposite the right angle, that would be the side that we call the hypotenuse. And so you could write down this law. Notice if you plug in 90 degrees to the cosine, you would get 0. And so this law of cosines does include right triangles as a special case. So do you see how by closing up angle C, this is angle C here, right now it's 90 degrees, but if you close that angle up a little bit, aren't you going to make the side length C smaller? See that here? This side is now shorter because we closed up the angle a little bit. And you can think of that as the purpose of this last term. We have to subtract off a little bit to reflect the fact that the triangle has closed up. It's no longer a 90-degree angle at that vertex down there. That's how I like to think about it. Let's use that now for this triangle. And I'll let you review the law of cosines if you don't see this immediately, but I'm going to think of this as my side C. This is what I called lowercase c in the previous image. So this here would be the angle capital C, and these sides would be my sides A and B. And let's assume now that we are talking about two waves of equal amplitude. The two electric fields from the two sources have equal amplitudes. So rather than call them E1 and E2, let's call them both E. And you'll notice I've labeled this angle now. These two angles have to add up to 180 degrees, of course. So if this angle is the phase difference between the two sources, delta phi, then this must be 180 minus delta phi, or pi minus delta phi. This is the angle that we would call capital C in the previous slide about the law of cosines. So here I've applied the law of cosines. I've said the side lowercase c squared, that's E total squared, that would be A squared plus B squared, which you see is E squared plus E squared, minus 2AB. So A times B is just E times E in this picture. So minus 2E times E times the cosine of the angle between sides A and B. Well, that angle is 180 degrees minus delta phi. And we're really close to the formula that we want. So what do we do next? What happens to the cosine function when you insert this pi minus? What have I just done here? Oh, I made a simplification first. E squared plus E squared, let's just call that 2 times E squared. And now we can do something with this cosine function. So I will remind you, let me pick a number to make this easier. The cosine of 30, for instance, versus the cosine of 180 minus 30. Well, what's the cosine of 180 minus 30? That would be the cosine of 150. So if this is 30 degrees and this is 150 degrees, you would still use this reference triangle, right? For the cosine of 30, you would use this triangle. For the cosine of 180 minus 30, you would use this triangle. The only difference is your adjacent side here is now negative. So this is the identity that we want. Again, I'm number picking, but the cosine of 150 is negative the cosine of 30. So let's turn this minus into a plus, and instead of pi minus delta phi, we'll just call it delta phi. Okay, that was a simple trig identity there. And now you see we can factor out 2e squared from the two terms. Just distribute that to get back to where we were. And then you may be recognizing this. There's a further trig identity we can use. It's this one down here. 1 plus the cosine of double an angle, all of that divided by 2, well, that's the same as cosine squared. By the way, am I the only one being bothered here by the italic font here and the non-italic font here? That's stressing me out. Let's see if we can find this in the previous slide. Don't forget there's got to be a 2 in the denominator if you want to turn this all into cosine squared. And all that really matters is that this angle be double this angle. You know, because sometimes you're going to encounter something different. You'll have x here and 1/2 x here. That's not always 2x and x. All that matters is that this angle is 1/2 of this angle. So I don't see a 2 in the denominator. Let's introduce a 2 and then pay for it by putting a 2 up top as well. So multiply and divide by 2, which means we're multiplying by 1. We're not really changing anything. That's where this 4 comes from. And let's use the identity that you just saw. I'm going to turn this into cosine squared, but the argument of cosine squared needs to be 1/2 of this argument. So delta phi over 2. Yeah, now this is starting to look familiar, isn't it? We're interested, well, I guess I'm going in circles here. First, let's find the total electric field. So take the square root of both sides. The 4 turns into a 2, e squared turns into e, etc. Great. So we've done it. We've actually found a general expression for the length of the total phasor. That's the intermediate case. Everything in between 2 times e for the case of max constructive and 0 for the case of perfect destructive. This is the total electric field amplitude for any phase difference. All you need to know is the phase difference. Divide that phase difference by 2, take the cosine, multiply by 2 times the electric field amplitude of each individual wave. Remember, this E is the amplitude of the individual electric fields. Both of those electric fields are oscillating in time. They're going positive, negative, but they have an amplitude. That's what E is. Well, how do we put this all together? I've already reviewed the fact that the path length difference here is the only source of phase difference. There's no delta phi sub 0 because the slits are being illuminated by the same laser beam, so there's no inherent phase difference. So you take the path length difference, you compare it to the wavelength, you multiply by 2 pi. So all of this could be plugged in there. But what's delta R? We've already seen that for the far field approximation, when your screen is far from the slits, or in other words, when the screen distance capital L is much larger than the slit separation lowercase d, then the rays are essentially parallel. You can use this expression for delta R. So first you would calculate this, plug it in here for delta R, and then you could plug that whole thing in for delta phi. Well, there's one more little detail we need. Remember the small angle approximation? When we're just looking at the maxima or the bright fringes near this forward direction, then the angles we're talking about are small. We can approximate the sine of theta by the tangent of theta. And you know what? This should not be an approximate sign. This should be equals. The tangent of theta is exactly equal to the y coordinate. That's the opposite side of that triangle divided by the adjacent side. So this really should say equals. The only approximation happens right here. Okay, so take y over L. This is, again, this is the actual coordinate of a point on the screen. We're interested in calculating the intensity at any y coordinate on the screen. So take y over L, plug it in for sine, plug that in right here, and then take this expression for delta R, plug it in right here, and then take that whole thing and plug it in for delta phi. Again, I don't have the whole result memorized. I just know how to do each individual piece. Once you've done that, it's just a hop, skip, and a jump, or really just the skip or just the jump to get from there to the expression we seek. Because remember, intensity of an electromagnetic wave, or I should just say intensity of light, is proportional to the square of the electric field. So you would square this total field here and then stick in your constant of proportionality. What was it? Speed of light, permittivity, maybe a factor of 1/2. But you're going to get an E squared in there. And we know that the intensity from each individual slit is proportional to E squared. So those same constants of proportionality would be out front. So do you see how that works? Once you square the whole thing, you've got your factor 4, that's right here, and then you've got your E squared, which is basically the intensity from each individual slit, once you stick in the constants of proportionality, and then you've got your cosine squared, and all this garbage inside the parentheses comes from the sequence of steps that I just outlined. So there it is. We have just accounted for, or derived, you could say, the intensity pattern as it depends on the location along the screen for two slits illuminated by the same source of light, like a laser beam. We have not accounted for the fact that as you move away from the forward direction, the intensity of the bright fringes actually drops off. That's coming. We'll do that in a future presentation. That has to do with the fact that each slit has a finite width. It's not actually infinitesimal. So there it is, cosine squared. Again, you have to rotate your normal way of thinking about graphs. The height of think of it this way. This is the intensity axis. This is the y-axis. Normally, we like to think of like y versus x. Now we're actually graphing intensity versus y-coordinate. So if you were back in high school algebra and you wanted to graph the relationship between two variables, think of intensity as being the vertical axis and the y-coordinate on the screen as being the horizontal axis. But now what we do is rotate that picture by 90 degrees to get this. So the y-axis actually goes this way and the y-axis goes this way. And we do that just to make it fit the way we normally draw the setup for the double slit experiment. We like to put the slits on the left and the screen on the right and ask how the intensity varies as we move up and down the screen. Okay, so but this is really a graph of intensity versus y-coordinate on the screen. And so this would be the value I equals 0. So this function is actually not oscillating between -1 and 1. Cosine squared oscillates between 0 and 1, and then we've scaled it up by a factor 4 times I1. So we've accounted for everything here. The peak intensity is 4 times I1. And why is that? Again, if you've got two slits, each with intensity I1 at any point on the screen, why wouldn't the total intensity just be double I1? Well, it's because the interference between the two waves, it redistributes the energy. It focuses the intensity preferentially at the bright fringes, and you've got destructive interference at the dark fringes. Now, what's with the 4? Again, we've seen that when the phase difference between those two waves is 0, the total phasor has a length of 2 times each individual phasor. So the field strength or the field amplitude will be double at places where they are interfering constructively, but intensity depends on the square of the electric field. So twice the field amplitude actually means 4 times the intensity. But as I mentioned earlier, if you look at the area, quote, under this curve, that means the area, when I say under, I mean in this direction. The area under that curve is the same as the area under this average intensity, because the total energy still has to be accounted for. So if you could add up all the energy falling at the bright fringes and in between the bright fringes, you would find it's still the energy coming out of the two slits. All that energy has to go somewhere. It's just being redistributed. It's not distributed uniformly across the screen. And when you see that interference pattern, you know you're talking about waves. Here's a nice graphic showing multiple slit interference. So you've got a laser beam illuminating various slits, which are all close together, and the screen is far away compared to the slit separation. But instead of just the double slit here, we're looking at the interference also for 3 slits, equally spaced, 4 equally spaced slits, etc. And they're even showing us what the light intensity would look like from one slit individually. This is the the so-called single slit diffraction pattern that we have not yet explained. That's coming soon. But you see it's got minima on either side of this so-called central maximum. It's a broad central maximum, but there are places on either side where the intensity falls to 0. And we've been pretending that a single slit alone would cast its intensity uniformly everywhere on the screen. So for an ideal slit, the intensity would be uniform across here. You wouldn't have these minima. And actually what happens, just a little sneak preview, the more narrow the slit is, the narrower the slit is, the wider, the more broad this central maximum becomes. So if you really did have an infinitesimally thin slit, this central maximum would spread out so far that it would look like just one bar of uniform thickness. Okay, let me point out just a couple things here, which will explain, we will explain this later. Do you notice that the spacing of the bright fringes for 5 slits is the same as the spacing for 4 slits and 3, etc. So it doesn't matter how many slits you have, as long as the spacing is the same, the spacing of the slits is the same, then the spacing of the fringes is also the same. We've already seen that for the double slit, if you change the slit separation or you change the wavelength, then the fringes will spread out or bunch together. But provided that you keep the slit spacing the same and the wavelength the same, as you add more slits, the spacing of the fringes stays the same. What does change is the way the intensity is focused. Do you see how these bright fringes are spread out compared to these? So the bright fringes here are more pronounced. They're sharper. Same with the dark fringes. They're more pronounced. So that's the general effect you see as you add more slits. And we're also going to explain that as well. If you went up to 20 slits, 50 slits, etc., you would find that the locations of the maximum become very sharp. The light becomes more focused there. Let's go into Python now for the first time and confirm that that cosine squared function really does give the dependence of intensity on position. And I'm going to do that by actually adding these phasors directly. I'll try to explain loosely what the syntax means here. Some of you with a programming background may be able to look at this and sort it out. And I will make these files available. Okay, first I have to import a library called NumPy so that I can use symbols like pi, sine, and cosine. If you try to use sine and cosine without those libraries, I don't think it works. And then we've got a plotting library, matplotlib. I think that's how you pronounce it. Okay, lowercase d, I've defined the slit separation. Here I went with 0.1 millimeters, right? 10 to the negative third is millimeters. So I'm just assuming SI units. And then for the wavelength, you know what? I thought I updated this with the actual Greek letters. So let me find that file instead. Okay, I've cleaned up this script just a bit by using actual Greek characters. So first I have to define the character pi as being the actual value pi, that's 3.14159, etc., using the NumPy library here. So np.pi, that's my shorthand for referring to the NumPy library, which has a bunch of constants and predefined functions. Okay, here I'm entering the distance between the screen and the slits, SI units, so this is 1 meter. N is the number of slits. Right now we're talking about the double slit, so I'll just go with 2 slits. And then I basically have to create an array of coordinates. If I want to graph something, I have to lay out, it's kind of like a row matrix of specific y coordinates at which I would like to evaluate the intensity. That's all I'm doing here. And when we do a lab using Python, you will not have to write any of this syntax from scratch. I'm just going to give you a template. All you have to do is tweak a few numbers. Trust me, nothing to stress over. And here I'm creating an empty array into which I'm going to plug the intensities eventually. So I haven't yet computed the intensity at each position along the screen. I just have to create this empty array that I'll plug the intensities into. And here's where I'm defining the function that actually calculates the intensity at a particular y coordinate. And I'm doing this with phasors. So I'm not going to plug in the cosine squared of pi y L over whatever it was. I'm going to use phasors instead. So first I introduced this symbol delta phi. That's the phase difference between the two slits. And you can confirm that what I've entered here is exactly what we already developed with the small angle approximation and treating the rays as parallel. You know, the path length difference delta r is d sine theta, and sine of theta can be approximated as y over L. Put all that together and you get this. And then what I've done here is create the x and y components of the phasor. So in keeping with my earlier presentation in this video, I probably shouldn't call them the x and y components. I should call them the real and imaginary components. These are the components of my total phasor, the horizontal projection and the vertical projection. So what I do is take each individual phasor and find its horizontal projection and its vertical projection, and then I add up the real parts and I add up the imaginary parts. Remember in the picture, you add up the two red projections from the two phasors to get the total purple projection of the total phasor. And then what I didn't talk about is how you could also add up the vertical projections of the individual phasors to get the total vertical projection. And then I just use Pythagorean theorem here. Once I've got the purple horizontal projection and then the total vertical projection, which I didn't highlight or talk about in the previous part of this video, I would just square those and add them up. And of course, I could take the square root to get the length of the total phasor. But remember, what's the significance of the length of the total phasor? That is the amplitude of the total electric field. And what we're interested in anyway, is the square of the total electric field. It's the square that gives us the intensity. So this function, intensity, you plug in a particular y coordinate on the screen, right? You plug in y, that's the argument of the function. And what comes out, what's returned here, is the square of the electric field, the total electric field. That's the amplitude of the overall phasor. Now, right now, this might seem a little overkill. I've got a for loop, for j in range of n, where capital N is the number of slits. But the reason for doing it this way is, you'll see in a moment, we can plug in any number of slits and it'll spit out the result the same. So this is much more general than just doing it for the specific case of two slits. Everything down here is just boilerplate stuff for preparing the plot. I have to decide what my horizontal axis, how far it reaches, maybe some color stuff. I forget exactly what I did here, but let's see how this works. And what I did have to, let me draw your attention to this. This is more complicated than it needs to be. I forget even why I did this exactly, some of this syntax here, but I would like to plot the intensity from one maximum to the next. That's just from one bright fringe to the next. We'll go back later and plot many more bright fringes so we can actually see the cosine squared behavior. But let me go ahead and hit run, and up pops the plot. Let's maximize. You can see I went so far as superimposing a horizontal line which shows the average intensity. So I don't know if you can read it, but this says intensity compared to I naught, where I naught would be the intensity from a single slit. So the average intensity across the screen is twice the intensity from one slit alone, but the actual intensity versus position varies from 4 to 0. So where the total intensity is 4, we're talking about the location of maximum constructive interference. That's the center of a bright fringe. And then down here where the intensity drops to 0 is the center of a dark fringe. That's where we get perfect destructive interference. Now, it's a little difficult to see that cosine squared behavior So let's go back and change the range to, how about instead of just one fringe to fringe distance, let's go with 8 of those. So I'll multiply by 8 here. And then down here for the plot range, I have to change that as well. And we'll hit run and see what the plot looks like now. It sure looks like a cosine squared function. We can even zoom in this magnifying glass icon, click and drag, you can zoom in. If I zoom in enough, it's probably going to get jagged. Hang on a second. If you hit home, I think it goes back to, yeah, so this is actually a pretty smooth curve, and that's because I chose 400 as my number of points. So basically it's connecting the dots. If I went with only 15 points, it's going to be a lot more jagged. Yeah, that looks terrible, especially when you zoom in. So if you go with a lot of points, it's obviously going to take your computer a little bit longer, but this graph is, it's not asking the computer for a whole lot of calculation behind the scenes. Let me pick an intermediate number like 100. I think it's going to look smooth at first. Even that's pretty jagged. How about 200? Okay, smooth enough, but if we zoom in on one of the peaks here, not particularly smooth. So to improve that behavior, to allow you to zoom way in and still see a smooth curve, just connect more dots. And 400 seemed pretty good because even when I zoom in, all right, we can see a little bit of jaggedness there. Okay, so what's cool about this? Well, first of all, I didn't actually program the cosine squared function, did I? I did it directly in terms of phasors. Now, previously I did this using a different library called, I think it's called SymPy, that actually allows you to do algebra with complex numbers. Because as I pointed out, a phasor really is just a complex number. You can use e to the I omega t instead of these cosines and sines. So I did it that way. And for whatever reason, the program was way slower. I found by just using the distance formula directly, these calculations get done really quickly. So let's make this more interesting and ask what the intensity versus position looks like for, let's say, 7 slits. Notice I haven't changed anything. Should I still do 8 cycles? Let's go back to just, how about 2? Let's look at a span of the screen between, well, I guess it's really 3 fringes. I'm going from one fringe to the next and then to the next. Okay, how does this look with 7 slits? Where's my graph? Hello? Invalid syntax. Ah, don't give me that. Okay, I had forgotten to give it the number of points with which to plot. Look how quick that was. Okay, a couple things have changed. I went with 7 slits, right? And you'll notice that the peak intensity is awful close to 50. In fact, it's 49. So 7 slits would mean that the amplitude of the total field at points of max constructive interference, in other words, in the center of the bright fringes, the total electric field amplitude is now 7 times what it was for each individual slit. Well, the intensity is proportional to electric field squared. So 7 times the electric field amplitude would actually imply 49 times the total intensity. And I didn't program that into the script, right? I'm just using phasors. What else do we see? Well, instead of that cosine squared, the part of the graph between the peaks is clearly depressed. It's been squashed down. So more of the power or the intensity is being focused at the bright fringes, and less of it is halfway between dark fringes and bright fringes. This is still the location of an interference minimum. Over here is another minimum, but previously the intensity decreased more gradually between the bright fringes and the dark fringes. Now it gets squashed more quickly. And there's another interesting feature. If we zoom in here just a little bit. Okay, here's a location of max constructive interference. I count not just one minimum between those two maxima. I count 1, 2, 3, 4, 5, 6. So there were 7 slits, or there are 7 slits, and I count 6, or n minus 1 minima in between those two maxima. Let's see if that pattern holds for a greater number of slits. How's about 10 slits? Oops, that's the screen distance. 10 slits instead of 7 slits. So the intensity is focused even more. See how the maxima are even sharper? I'll zoom in and count the number of minima in between maxima. 1, 2, 3, 4, 5, 6, 7, 8, 9 minima. So 10 slits, 9 minima. It does appear that this pattern holds in general. And maybe you noticed that curve was starting to get a little jagged. So I'm going to put even more points in there and ask it for something crazy like 50. Let's see what happens. Whoa. So there's a clear trend here. The more slits you add, the sharper the interference maxima get, and the more minima there are. Now these are so squashed, I don't think we're even going to see much. I've already forgotten, was it 50 slits? Yeah, 50 squared is 2,500. How many minima do you think there are here? I would expect 49, but I'm not going to count them. We'll come back and do much more with Python in our investigation of wave optics.
Shields are being drained. 90%? 80.
Trying to recalibrate nutation. Damn!
Shields have failed. Fire all weapons.
Their subspace field is intact. New phasor frequencies had no impact.